Okay, so today we'll talk about, we'll be able to discuss on how we can approach those ladder questions. So those questions are often asked, and you need to be to pay particular attention as you answer those questions, but they are quite easy. Okay, so I beg to be corrected. Did we do any of the questions from the tutorial sheet on those ladder ones?
No.
Okay, so if we didn't do any, then we can start with question number, is it number 4? We can start with question number 4. We see on how we'll do that. Then we'll be able to move to question number 5 as well. Let's see how we can attempt that. And you should know that those 2 questions which were put in the tutorial sheet, there are 2 cases where a question could be asked like that one on question 4, and there's also a case which in which a question can be asked like that one in question 5. Okay, so you should not combine the 2 scenarios. So let us start with question 4. We see how we can attempt question number 4. So on your tutorial sheet 8, question number 4 is saying a uniform ladder for 5 meters long, weighing 200 newtons, is leaning against a frictionless vertical wall with its base 3 meters long from the wall. The coefficient of friction between the bottom of the ladder and the ground is 0.45. How far measured along the ladder can a 600 Newton man climb before the ladder starts to slip? Before the ladder starts to slip. So we can draw that sketch that we have. So the sketch that we have looks like that. This is a wall and this is the ground that we have there, and we have this ladder here. We have that ladder there. Okay, so we have a force here. If we want, we can show it here, there's no problem. Okay, we can call this force as wall force. So this is the force exerted by the wall force. Then here, this ladder, as it leans on this ground here, okay, it will be trying to move in that direction, but there will be some force which will be opposing its motion to move in that direction. And this force, we call it the frictional force. Okay, the frictional force in this case will be pushing this ladder to this direction. Okay, so we'll have frictional force in that direction there. Okay, so apart from the frictional force, we also have the force which the ground exerts on the ladder. We have the force that the ground exerts on the ladder, and that force, we call it the normal force. We call it the normal force. So if you want, you can show it at the top, or if you want, you can show it here. There's no problem. We call this as the normal force. So this is the normal force here. Okay, so apart from that, we also have the weight of this ladder, which is concentrated at its center. So we assume this is the center of the ladder. And a man also climbs on this ladder somewhere here. Man is somewhere there. So that is what we have. So these are the weights of the man and the ladder. Okay, so we have been told to say how far measured along the ladder can a 600 Newton man climb before the ladder starts to slip. Okay, so actually what they only want here is the distance from this ground here. Okay, so we'll take our pivot to be at the ground there. That's what we'll take as our pivot. So this distance here is the distance they want. Okay, this distance here. This is the distance they want you to find there. Okay, so questions under equilibrium can be solved using two conditions. And those conditions are the sum of the forces should be equal to 0, both forces in the X and in the Y. And the second condition, the summation of the torques should also be equals to 0. So you should play around with these two conditions for you to get your answer there. Okay, so we can move in that direction. So here, if we take our torque to be at the bottom there, yes? Is that a question?
Can you just write for me what you're from saying?
Okay. Okay, we're saying that questions here could be solved using two conditions. The first condition is that the sum of the forces should be equals to 0. Okay, so these forces are forces in the X should be 0, and also forces in the Y should be equal to 0. So this is the first condition. This is the first condition here. The second condition is the summation of the torques should be equals to 0. That's the second condition. Okay, so this is the only way you will be able to solve this with the help of the angles. You work within these two conditions, and when you are dealing with equilibrium questions there. Okay, so we can try to proceed. So we'll have torques caused by this weight here, the weight of a ladder. We have been given that it is 200 newtons. The weight of a ladder is 200 newtons. And okay. And also the weight of a person is 600 newtons. The weight of this person is 600 newtons. Okay, so that's what we have. So we have the torques caused by the 200 Newton force, torque caused by the 600 Newton force. We also have the torque caused by the wall force, the torque caused by the wall force there. Okay, so if you try to sum your forces, okay, wonderful. So if you'll be able to think about it, this force here, it is also a kind of normal force. This force here, which is exerted by the wall on the ladder, because the normal force is exerted by the surface on an object. So in that other cases, you find to say that this wall force, it is also a normal force, but this kind of normal force is along the X direction. This kind of normal force is along the X direction. Okay, so for us to be able to find this wall force here, for us to find the wall force here, it means that we have to sum the forces along the X. Okay, we have to sum the forces along the X. So write this condition here, the summation of the forces along the X will be equals to 0. Okay, so here we are trying to find, because we need the torque caused by this force here, the wall force, but we don't know the value of that wall force there. We don't know the value of that wall force there. So for us to find this wall force, we need to sum the forces along the X. And along the X, we have this same wall force, the normal force along the X, being applied to the positive X direction there. So that force will be a positive force. Okay, it will be a positive force minus this frictional force here, which is pushing to the left. Okay, this is a negative force because it is pushing to the left there. So you have the frictional force there carrying a negative sign, and this should be equals to 0. So if we add these two forces, they should give us a 0. But remember that we can find the value of the frictional force. Okay, we can find the value of the frictional force. So we can simplify this equation further by simply saying the wall force is equals to the frictional force. The frictional force here, right, this here, the frictional force, we can replace with an equation for the frictional force. Remember that frictional force is given by mu multiplied by the normal force. Is given by mu multiplied by the normal force, that will give us the value of the wall force there. So we've already been given the value of the coefficient of friction, which is the mu. We have already been given that value, which is the 0.45. 0.45. That is the value of the mu there. Okay, so we need to find the normal force. Now, for us to get the normal force, it means we need to sum the forces along the y. Okay, we need to sum the forces along the y. So I will raise this top part so that we relate with what we are talking about. Yeah, so sum the forces along the X, and we found that the only forces acting along the X, we have the wall force, and we also have this frictional force, the only forces along the X. Now, along the Y, the forces that are along the Y, they should also equal to 0. They should also equal to 0. So along the Y, we have this normal force exerted by the ground. It is pushing up, therefore it will carry a positive sign. So we'll have that value there, the normal force minus the weight, 200 Newton, is acting downwards, it is negative, therefore, and also the 600 Newton force, and these will be equals to 0. Those will be equals to 0. So if we add these two, what value are we going to get? So we should do our evaluation here and take the value to the other side of the equal sign. What value are we getting from there?
800.
800.
800, okay. 800. So that's the value we get, 800 Newton. So this is the value of our normal force. You can replace it here. So where there's Fn, you put your 800. This will give you the value of the wall force. This will give you the value of the wall force or the normal force exerted by the wall. And what is that value? Okay, 360. 360 Newton. So this is the force exerted by that wall there. That is exerted by that wall. Now, from there, we can proceed to summing our torques. We can proceed to summing our torques so that we find the displacement of the man. so that we're able to find this distance here. So we can call this as D. We can call that as D. Okay. So I'll erase this part and erase this part so that we have reference of our sketch there. Okay. Wonderful. So I'll also erase these forces, but just know that we have the frictional force and we have the normal force here, so that we deal with the torques and see the kinds of displacements we'll be applying there. Remember that the torque is the sum of, is the product of the force and the perpendicular distance. Okay, so this is the concept or the definition of the torques, which should help us to calculate the torques there. Okay, so someone is asking about the wall force. Okay, so this wall force, it is the same as the normal force. Huh? It is simply a normal force itself, but this normal force is exerted by the wall. Okay, this normal force is exerted by the wall. It is the normal force. There is no harm in calling it the normal force. Okay, so like I was saying, for us to calculate the torque, we need to have the force and the displacement perpendicular to each other. So if we were to extend this 200 Newton force, it will be perpendicular to some distance here, because the torque, we are taking the torque to be here to the ground. So this distance here will be the displacement of the 200 Newton force. Okay, then if we were to extend this, we try to extend it here, the perpendicular distance is this distance here. Okay, is that distance there. Then for the normal force there, which is called the wall force, the perpendicular distance is this distance here. Is the distance which is perpendicular to it. Is the distance which is perpendicular to it. Or if you are not comfortable in showing it this side, it is also fine if you show it from the pivot. It goes like that. There is no harm. Okay, there is no harm. Wherever you would want it to put it, if you want to put it here or on that other side, there is no harm. Okay, so that is what we have there. That is what we have as our distances. So we can call this as x1, we can call this as x2, we can call this as x3. Okay, so now we can proceed to summing our torques, and it should be equal to 0. Our torques should be equals to 0. Okay, so that is what we shall have there. You'll be able to agree with me that the wall force here, okay, it will cause a torque in that direction. It will cause an anti-clockwise, it will cause a clockwise torque. So it will cause a clockwise torque. Post these two, the 600 Newton force or weight and the 200 Newton weight, these will be able to cause a clockwise, an anti-clockwise torque. They will cause an anti-clockwise torque. So these 200 and 600, they will be positive torques. There will be positive torques. So we can start. Yes.
I have a question.
Go ahead.
On the way you have mentioned clockwise and the anti-clockwise. You're saying the FW is the anti-clockwise or clockwise?
This one is clockwise.
But isn't it going in the downwards direction?
Yes.
Like according to the arrow that you have drawn.
Exactly. So that's the direction of the of the torque. Huh? That's the direction of the torque. It will move like that. The torque will move like that. Okay, so this is the direction of a clock. Okay, this is the direction.
But isn't
of
that
clock.
anti-clockwise direction? Like
Come
the
again?
way it's moving downward. The way it's moving downwards, isn't that anti-clockwise?
Clockwise is the other way around. Clockwise is like that. Anti-clockwise, sorry. Anti-clockwise is this one, then this is clockwise. Okay. Like that, it will cause anti-clockwise torque. Then this one here will be a clockwise one.
So didn't you say that clockwise is the way the clock moves?
Exactly.
Like,
yes.
this doesn't the clock moves? Isn't that clockwise the way the clock moves?
Okay. If we move like that,
Okay, sir, thank you. I've understood. I've
okay.
remembered how it moves.
Okay. Okay. All right. Okay, so we proceed. We can start with the summation of the torques for the 200 Newton weight there, for the 200 Newton weight. So we already know the displacement of this base here. The base, we already know the displacement, and we're told that it is 3 meters long. It is 3 meters long. So because it is 3 meters long, this 200 Newton weight is acting at the center of this same displacement. Okay, it is at the center there. It is acting through the center there. So because it is 3 in displacement long, then from the pivot to where this 200 Newton weight is acting, the distance there, which is x1, will be equals to 3 divided by 2. 3 divided by 2, because the 200 Newton weight is at the center. Okay, is at the center. So we can simply divide that length by 2, and we'll be able to get the value of x1 there. The value of x1, and what will that be? Is it 1.5? 1.5. So this is in meters there. That is in meters. So we don't know the value of x2. We don't know the value of x2. Okay, so this question is in your tutorial sheet. It's tutorial sheet number 8, question 4. Question number 4. Okay, so we don't know the value of x2 here, so we'll leave it the way it is. But I'm sure we are able to find the value of x3. Do we know the value of x3?
Yes, we can find it.
Okay, how can we find it?
So it was given in the question, wasn't it? Or we can find.
I'm sure that one.
Since we are given the.
Yes.
Since we are given the two sides.
Okay.
We can use Pythagoras there.
Yes, we can use the Pythagoras theorem. So we have been given this longest part of this triangle. We can consider it as a triangle now. this longest part of a triangle, we've been given that it is 5 meters. Okay, so that is a ladder which is 5 meters. The base here we've been given to be 3 meters long also. Okay? And we can find this wall, the length of the wall here, which is the x3, using the Pythagorean theorem. Okay, so if we use the Pythagoras theorem, how will be our equation? What will be the Pythagoras theorem?
Squared
Come again?
minus 3 squared 2. 5 squared
5
minus
squared
3 squared 5
minus
squared minus 3 squared is equal to x3 squared.
Okay.
X3, that one.
Squared. Wonderful. Okay, so that is what we have here. You can actually call this side, you call the ladder side, you can call it your A. Okay, you can call it as your this side, your B. Okay, so if this is A squared minus A squared minus B squared, okay, equals to x3. Or we can call it C, fine. That is what we shall have. Okay, so from there, what will be our x3?
4.
It will be 4. Okay, so if you add these two, you square them, and the square root, for us to cancel out this square, which is on x3, you have your x3 to be equals to 4 meters. To be equals to 4 meters. Okay, so we can now use the torque equation for us to get the x2. For us to get the x2. So we move in that direction. So we raise this. Okay. So the summation of the torques will be 0. Will be 0. So here we have the torque caused by the 200 Newton weight multiplied by x1. We've been told that x1 is 1.5, then plus 600 Newton multiplied by x2, which we don't know, then minus the wall force. What was the value of that force there?
360.
360. So 360 multiplied by the 4, okay, that we found there. And this should be equals to 0. Okay, so if we find the value of x2, if you evaluate that and make x2 the subject of the formula, what answer are you getting?
1.9.
1.9. Wonderful. So the value of x2, not x3, value of x2 is 1.9 meters. So I found this x2 here to be 1.9 meters, but we're not interested in x2. We're interested in this top part there, which is the D that we've called the D. That is the part we are interested in, okay? So for us now to be able to get that part, we can try to find the angles. We can try to find the angle. So this one here, it will be considered as our hypotenuse, the D, okay, to be considered as our hypotenuse. And this down part here could be considered as our adjacent. It could be considered as our adjacent. So I'm sure you're able to observe that we can find the angle here in our sketch. Yes, please.
Why are we subtracting 360?
Okay. It is causing a clockwise torque. Huh? This one here, this 4 force here, we found it to be 360. Okay. So the torque.
But the clockwise.
Okay. Okay. Okay, so we can try to proceed. So let me clean up this inside part of our sketch here. This part here. So we can find this angle inside here. We can find this angle inside here. We already have the hypotenuse and we already have this adjacent, which is down here. We can use it to find the theta inside there. We can use it to find the theta inside there. So I'll move to the next screen. So we'll be able to find that our theta, if we use SOHCAHTOA for us to get the angle, we'll be able to find that the relationship which relates adjacent and the hypotenuse will be the cosine function there. So say cos theta will be equals to our adjacent is 3 meters. Our hypotenuse is 5. Our hypotenuse is 5. So from there, we can make theta the subject of the formula and say cosine inverse 3/5. Okay, so from there, what will be the value of your theta?
$53.1.
53.1. This is in degrees, 53.1 degrees. Okay, so if we were to cut this sketch here, remember that 1.9 we found is x2, and x2 ends somewhere here. So if we cut our triangle here, like that, we'll have a small triangle inside there, and we can work on that. Okay, we can work on that. So let us redraw that same triangle here. We can draw it like this. Okay, so that is what we have there. We have our angle here to be 53.1. We have this side D, which we don't know. And we have this side here to be known as 1.9 meters. Okay, so that is what we have. So now for us to find the hypotenuse now, what can we do?
I don't know, but I think I'm finding a different figure here.
Hello, come again.
I'm finding a different figure
Okay.
on inverse cos 3/5.
You can use the cosine function.
Okay, so you do you divide the 3 divided by 5. If you divide that, then you can find the cosine inverse of that. Okay. Because I'm sure if you divide 3 and by 5, you have 0.6 as your value. You have 0.6 as your value. Then you can find the cosine inverse of that.
Okay, sir. Thank you. I was computing it wrong.
Okay. You're welcome. So now for us to get this value,
Cos
yes,
cos 53.1 is equal to
cos
53.1 is equal to 1.9
1.9
over D.
okay,
Over D.
over the D. Okay, so where this is coming from is that look at this triangle that we have here. This triangle here, we are trying to find the hypotenuse. Now, for us to get the hypotenuse, we resort to SOHCAHTOA. Okay, we resort to SOHCAHTOA. So here we have the adjacent and we want the hypotenuse. So we are using cosine function. Okay, so we are using cosine function. We have simply said cos theta is equals to the adjacent, which is 1.9 divided by the d. This is the equation that we have. The theta is 53.1. Okay, so our meeting is about to cut. When it cuts, you join again. Then what will be our d?